Another use that we can put for these values, these measurements of crystal structures, is this one. So let's say we have iridium. It has a face-centered cubic unit cell with an edge length of 383.5 picometers. It says the density of iridium is 22.61 grams per cubic centimeter. We're going to use this data to calculate a value for Avogadro's number. Do you realize that we probably never really discussed how Avogadro's number was found? I think I may have mentioned it earlier on, but there's actually more than one method that we can use to find Avogadro's number. Let's go back here to our whiteboard, and let me put in a paper version of what we were just looking at over here. All right. Let's see if our fabulous camera and internet thing here holds up. Okay, there we go. Okay, no, that didn't work. All right, let's see if I can zoom in a little bit. Oops, not so much. Whoop, not that bad. Okay, so there is our problem. And let's see how we approach this. So the first thing is, we see that this is a face-centered cubic cell. So that means it should have 4 atoms per cell, correct? That's what we discussed earlier on. You can see the pictures here. Remember, it's essentially each particle in the corner is being shared with other cubic unit cells. So only 1/8 of each one of those particles is inside the cell we're studying. So we have 8 times 1/8. And then the ones on the face are each shared with another adjoining cubic cell. So only 1/2 of each one of those 6 positions are included. So we have 4 atoms per cell. Now, the other thing we're going to need here is we need to find out what is the volume of this cell. Well, remember, the volume for a cubic cell is, again, width times the height times the depth. In other words, the cell edge length cubed, correct? So it says here that the edge length is 383.5 picometers. But again, we would like to convert that into cubic centimeters, right? So remember that we said that 1 cubic centimeter is 10 to the, what did we say? 10 to the 10 picometers. And all of that now has to get cubed, correct? So that is roughly about 5 point, actually, no, I have that wrong, I'm sorry. It's actually 3.835 times 10. Oh gosh, what am I doing here? Sorry, guys. This is equal to total 5.640 times 10 to the minus 23rd cubic centimeter. I'm sorry about that mess. I misread my notes. Okay, the density is, we're told, is 22.61 grams per cubic centimeter. And remember, we're going to use the same trick we did before. We're going to calculate, well, what is the mass inside the cubic unit cell, which is 4 atoms. And because this is iridium, we can look up in the periodic table, it has a molar mass of 192.22 grams per mole. So let's build ourselves a pretty fantastic dimensional analysis thing here. So we have 4 atoms in one cell, right? We said that because it's a face-centered cubic arrangement. We know that one cell has a volume of 5.640 times 10 to the minus 23rd cubic centimeters. We know that in 1 cubic centimeter, we would have 22.61 grams of iridium. Let's see how we're doing here with the units before we proceed. Let's cancel out the cells, cancel out the cubic centimeters. So what I want now is I want to put in the molar mass. We have 192.22 grams in 1 mole of iridium. That cancels out the grams. And what are the units left when we do all this? Atoms per mole. In other words, Avogadro's number. So I'll let you guys, if you want to play with that for a moment in your calculator, and then I'll write down what I got. Yep, I get, again, this is an exact count. So I'm going to go, typically, either the density or the edge length are going to be the giveaways in terms of sig figs. So both of those have 4 sig figs. So let's write it to 4 sig figs. I get 6.029 times 10 to the 23rd atoms per mole. Not bad, huh? Pretty close to the official Avogadro number that we have been using all along, which was 6.022 something times 10 to the 23rd. All right. So what's interesting is that, again, I am not personally an expert in X-ray crystallography, but talking to some of my colleagues who are, it's very interesting. But if you repeat this kind of analysis with almost any kind of element that forms any kind of cubic unit cell type of structure, and you find out what is the edge length and you have their density, you are going to be able to get Avogadro's number every single time with a very, very small percent of difference. It's a very interesting thing. So don't know if you're going to get this kind of practice exercise in your homework assignment, but if you don't, there it is. I will scan this and post it with the recording on your lecture notes in Canvas. Okay, I'll leave it there for a few more seconds so you guys can look at it, and then we'll come back.